So in experiment 1, it was all about measurements, but now you're gonna analyze and see which of the glassware like pipette, graduated cylinder, and burette is the best for measuring volume. And of course, that would have been used together with the analytical balance, where you'll get masses of this glassware, of the liquid from this glassware, and then use the mass and the volume of the liquid to find density. So whichever glassware that results to a density very close to 0.99691 grams per centimeter cubed, that will be the best glassware, because the lab temperature has been 25.5 degrees this week, so the density of water should be this. Okay, so you'll be taking volumes of water using this glassware respectively, get the mass of that water, of the 20 ml volume of water, using a balance, and then of course, you know the volume, you know the mass, you find the density. The glassware that gives you the average density close to this is the best. Other than using this equipment, you're also shooting for accuracy, which is how close your answer is to the known density value, and you're shooting for precision, which is how close are your numbers, the trials. You'll do trial 1, 2, 3, how close your answers are to each other. Okay. And to measure the closeness or precision, we'll use standard deviation and percentage standard deviation, and another one, percentage relative error. So we'll talk about that as we go. Alright, so the lab temperature, like I mentioned, was 25.5. So the density of the distilled water should be roughly 0.99 grams per centimeter cube. And we are going to take advantage of finding the density using the masses of liquid obtained from different glassware, obtained by measuring the mass of 20 ml volume measured using these three glassware. Okay, so I'll talk about accuracy, how close the measurement is to the accepted known value, which for us will be 0.99691. Precision is just how well the multiple measurements are close to each other. So looking at this student, they did measure a volume of a liquid and took that volume and measured its mass. So mass divided by volume gives you the density. So for each trial for student 1, he got that. You add these 3, divide by 3, this will be the density. This line here just implies that it needs to be 3 significant figures, but you don't round up yet or round off yet. Student 2 did the same thing, got that. Student 3 got that. So if this liquid, if this unknown substance had a density of 0.855, which student is the most accurate? So to know who is the most accurate, you will subtract their averages you'll subtract the known from the averages. Okay, so student 1 obviously is 0.89, this is 0.85, that one is not accurate. Okay, this one is not accurate. Then 0.8567 is very close to 0.85. So it seems like, just looking at the average, this student 2 is the most accurate, although student 3 is also accurate because the difference between 523 and 55 is very small. So we'll generally say student 2 and 3 are accurate, student 1 is not accurate. The reason why you'd lose this accuracy is because of what we call systematic error. Okay, his numbers are close, they are precise, but the average is wrong. Okay, he's precise but not accurate, so he got an error that kept on showing up. So that's an error that shows up from maybe a faulty balance or faulty glassware, and he used the same balance, so he kept consistently experiencing the same error. So that's systematic error. Random error is like this student 2. Let's see, random error, probably comparing these two values, that could be a random error. because they are not precise. Even though the final average is accurate, these numbers are so different. Probably the student poured out some liquid. Okay, he just by chance ended up getting an average that's accurate, but the actual data entry is not accurate. Okay, so student 2 was not precise, but definitely he was lucky enough to get an average that's very accurate. Student 3, on the other hand, is both accurate and precise. If you look at the numbers, are close enough. At the same time, we say it is accurate. So you want to be both accurate and precise. Student 3 is the best out of these numbers. Now, that is using eyeball. We need to use calculations to really prove that student 1 was precise and not accurate. Student 2 was accurate and not precise. Student 3 was both accurate and precise. So we use statistics by comparing the standard deviation, which is just how much the individual trial in an average deviates from that average, and using the deviation. These two terms or these two quantities will help us determine whether a student is precise and accurate. Okay, so let's look at student 1. Here is student 1 with his densities. Obviously, this was the average. You just add up the densities divided by 3. So this D is not density, this is deviation. Okay, so you do the average minus the data entry. So the average is 0.8907, subtract 0.8907 minus this value, you should get this value. Square it, you get deviation squared, which is this value. You square this, okay? Square this top value, you get that. Square this top value, get that. Square this top value, get that. Again, the deviation is just the average minus this gives you that. Okay? So using d squared, you can find the standard deviation. So add up your d squareds depending on the number of trials. That's what n is. For our case, the n is 3 trials. N is 3 trials. So add up the d squared divided by 3 minus 1. Do the square root. The standard deviation is 0.004. Do the same thing for student 2. This will be the S. Student 3, this is the S. So as you can see, the most precise student turns out to be student 3 because he has a low standard deviation. Okay. In terms of accuracy, one will do a percentage. If you want to know the accuracy, you do the percentage relative error. Okay, you look for the percentage relative error. This is the average, or what you call the mean. Y is the actual value. So for these students, the actual known density of their liquid was 0.855. So you would put 0.855. That's what they expected to get if they had no errors. And then the mean of student 1 is this one right here, 0.89. All these are means, they are the averages. So you put that one here where there's an x slash, that's the mean. Subtract, divide by the same actual, which is 0.855 times 100. You'll find that student 1 has 4.2% relative error compared to the rest, which are less than 1. So you can see student 1 was not accurate because relative error tells us whether the student is accurate or not, and you'll be calculating that. So you can see student 1 was not accurate, student 2 was not precise, the numbers were far randomly spread. You see 0.7, 0.9, 0.8. Student 2 is not precise, and lucky, good enough for student 3. He's both precise and accurate. Now to get the percentage RSD, you just take your standard, divide by, this is divide by the mean times 100. So the bigger the percentage, the poorer the precision. So student 2 is not precise because he has 14%. you can see these two guys are under 1%, they are precise. So student 3 is both precise and accurate. Student 2 is just accurate and not precise. Student 1 is not accurate, he is precise. You want to be student 3. So you'll need those calculations. If you scroll down where your data table is, you scroll down in your report sheet where the data table is, that's the calculation that's going to be done on this part. All right. So how do we go about doing the experiment? So you'll start with the flask. Okay, you can read the report, it tells you what to do. You can read the manual. So you'll take a flask, you'll take a graduated cylinder, because you're testing the graduated cylinder, the pipette, and burette. And then measure 20 ml as described in the procedure. I won't read it. You know how to read, you read what the procedure says. And then you would transfer this 20 ml in an air flask. But before you transfer, the air flask is weighed with a stopper, so the mass will be written here. So let's call this M1, which is the mass of the empty flask. Okay, this empty flask plus stopper. Then take your 20 ml from your graduated cylinder, pour it in here and weigh again. So you have the stopper with your flask. This time you have the liquid in there. So you weigh it. So here is gonna be the mass here is gonna, let's call it M2. Okay. So in this case, the only thing you've introduced is the liquid, the water, which happens to be 20 ml. Okay. The 20 ml is poured in there. You used graduated cylinder to read 20 ml and transferred it in there. So how do you get the mass of water? It's gonna be M2 minus M1. Okay. Remember the volume was 20 ml. So to find the density, it will be the mass all over volume. In this case is M2 minus M1 divided volume. Remember your graduated cylinder has readings of 1 like this. Let me show you. This is, I'll send you a video on this and you'll see. So if this is 0, this will be 10. So in between each single line, like we discussed in experiment 1, is 1 ml. So a tenth of 1 is 0.1. So if this is 20, so you need to write 20.0 plus or minus 0.1 as described in experiment 1. That's the uncertainty. So it should be the same thing here, 20.0 plus or minus 0.1 ml. 20.0 plus or minus 0.1 ml. Remember, you're reading the bottom of your meniscus. So assume this was 20, then the meniscus will be touching the 20 line like that in your graduated cylinder. So your eye is reading that way. Okay. So that will be testing the graduated cylinder. Then do the math. I've shown you how to find the deviation squared, the S, this and this. So the one that gives you the least relative error, least standard deviation will win. So we want to check, will the graduated cylinder be the best glassware to measure volume based on the answers we get from standard deviation here using density as a determining factor. Okay, will the graduated cylinder win? Will the pipette win? Or will the burette win? That's the goal. Okay, so now for the pipette, it looks like this. Okay, the manual tells you to use the 20 ml pipette. Usually we use a pump. You don't want to use your mouth, so we usually use a pump which looks like a syringe. So the syringe has has a wheel where you can just rotate the wheel. This thing will go up or go down by rotating the wheel. As it goes up, you're sucking in the liquid. So it's usually taken in up to a point there. There's usually a mark, the 20 ml mark. So you'll take that and you're going to transfer it into a pre-weighed dry flask. Okay, so again, let's call this M1 because this is just your stoppered flask, stoppered LMR flask. And then deliver this liquid into the flask that you weighed on a weighing balance. So let's assume that's the liquid. Weigh again. The flask stoppered water, which is your liquid, get M2. So mass of water, which is the only difference, will be M2 minus M1. Of course, the volume was 20 ml. Because this instrument has no calibration, we leave it as an exact number. No need to show standard deviation. So to get the density is very simple. You have your mass, you have your volume. So density is mass all over volume. You'll get your answer for trial 1, trial 2, and trial 3, and proceed with the deviation calculations stuff on there, your standard deviation up to down there. So for the burette, it's slightly different. The burette, you read it from the top to the bottom. So it runs from 0 to 50 ml. Now it tells you to get 20 ml. So assume that your liquid is right here and assume you're reading this as 1 ml. Remember again, the burette has 10 baby calibrations in between each unit. So if that's 0 ml, this is 1 ml. So each of these lines is 0.1. A tenth of 0.1 is 0.01. So the uncertainty for the burette must be plus or minus 0.01. So if this meniscus is sitting right on 1, then my initial volume will be recorded as 1 with 2 decimal digits after the decimal points, 2 digits after the decimal point, plus or minus 0.01. Okay? That's my initial. Now I need to get 20 ml out of the burette. So I will have to empty out a liquid of 20 a liquid with 20 ml volume. So the way to know where to stop is to drain this up to where it reads 21. Okay? Up to where it reads 21, which means I will have delivered 20 ml. I will have delivered 20 ml. Starting from 1, if I stop at 21 and collect the liquid that I've drained by opening the tap, I'll have collected 20 ml. Alright, so the final volume here should be 21.00 plus or minus 0.01 in order for me to collect 20.00 plus or minus 0.01 ml. Okay, so this total ml is the difference between where you started and where you stopped, because this is the initial volume. Add 20, you drain the liquid up to 21. That's the final volume. The difference gives you the volume you collected in your beaker. Okay? So that flask, this liquid would be transferred into the flask. And in fact, the best way to do it is not to collect in the beaker. The best way to do it is to weigh your flask again in the stopper, and then take that flask and collect the liquid directly, because you don't want to keep transferring liquid. Okay, cover the stopper, the flask with the stopper, and weigh. You're gonna get the mass here. So let's call this M2 and let's call this M1, where the water is not in there. After weighing M1, you move the stopper from the flask and collect your 20 ml as described. If your initial is 1, you need to drain up to 21. That's how you collect the 20. And then stopper the flask and then weigh again. You're going to get M2 mass. The difference between M2 and M1 gives you the mass of water. So this is the volume of water, which is the difference between these two guys. The density will be M M2 minus M1 divided by the volume, right? Because M2 minus M1 gives you the mass of water. We know that density equals to mass all over volume. So I'm just going to say M2 minus M1 divided by the volume. Do you know the volume? Yes. The volume is 20 ml. This one depends on what you're provided up there or what you'll find. Once you get the densities on the three, you can get the average and then do the standard deviation as described. Remember, the goal is to compare the graduated cylinder with the pipette and the burette. Whoever gives you the most precise and most accurate density, that will win. So your accuracy depends on the average. Remember, I said your densities must be close to 0.99691 grams per centimeter cubed, because our lab, collecting the data from our lab, this should be our density for water. This is your Y. That's the actual. It's the Y. I'm calling it Y because you're going to need it here. Let me show you where you'll need it. You'll need it to calculate relative error, which calls for which glassware is the most accurate. So it's coming. Okay, so our Y is not 0.855. Your Y, which is the expected density at our lab temperature, the expected density of water is 0.99691 grams per centimeter cubed. That's going to be your Y. Use that to determine the percentage relative error, which decides which glassware is accurate. So the glassware that gives you the least relative error, given that you are shooting for 0.99691 density of water, that will be the glassware that will win according to your data tables. So accuracy will be dictated by the relative errors. That guy, compare that to this for the pipette and this for the burette. Whoever gives you the least percentage error is the most accurate glassware. But again, whoever gives you the least percentage RSD of density is the most precise. So the glassware that is most precise and accurate will win. So out of these calculations, you want the glassware that is both precise and accurate. Remember again, your density of water, the expected actual density of water should be 0.99691 grams per centimeter cubed. How do I know that? Remember where I started the lecture, I told you that the temperature of the lab has been 25.5 this week. So the density of water at 25.5 is known to be 0.99691, not 1 gram per centimeter cubed according to textbooks. It depends on the temperature. Our lab temperature is 25.5, so you are shooting to get as close to this as possible. So that is your Y to calculate the percentage relative error. All right, so go for it. All right, so when you're done with your data calculations, this report sheet should be turned in Moodle, and you answer the questions on this report sheet to be turned in through Moodle. Okay, you have your report sheet in your manual, and a copy of the report sheet is posted on Moodle under chapter 2. Okay, so the report sheet must be answered and turned in. This is the pre-lab. Let's see, where's the report sheet? The report sheet starts here. You have to turn in the report sheet with the data table. Copy of the data tables are on Moodle somewhere. It says data tables on Moodle. All right.